Hey there, and welcome back. If you've been following along, you've done something pretty incredible. You've seen how we can build a computer from the absolute ground up, from simple logic gates all the way to a processor that actually runs code. But now we have to ask the million-dollar question, is it actually fast? Let's find out.
You get the core logic now, that whole fetch, decode, execute cycle. But here's the thing. The simple computer we've pieced together in our minds feels like it's from a whole different universe than the supercomputers we carry around in our pockets. So, is our simple model fast enough for the modern world? Well, the short answer, no. Not even close. And figuring out why? Well, that's basically the story of all of modern computing.
I mean, just take a look at this chart. It really shows you the insane scale of this performance jump. Before the mid-'80s, things were growing at a nice, steady 25% a year. But then, from '86 to 2002, something big changed. Performance growth just exploded to over 50% a year, all thanks to some brilliant new ideas in architecture. The result? A modern chip like an Intel Core i7 is, and I'm not exaggerating, tens of thousands of times faster than its ancestors. So how on earth did we get from here to there?
To really understand that leap, we first have to get what was holding our simple model back. And it really boils down to two fundamental problems. These two big villains that computer architects have been fighting against for decades.
Okay, so villain number one is the sequential bottleneck. You see, our simple model is super neat and tidy. You fetch an instruction, you execute it, then you go get the next one. It's like a single file line at the grocery store. One person checks out, then the next, then the next. But this one-at-a-time approach creates a hard speed limit. You're fundamentally limited by how fast you can process just one thing at a time.
And we can actually put a number on this using a metric called cycles per instruction, or CPI. For a simple processor like ours, the absolute best you can ever hope for is a CPI of 1. One clock cycle for one instruction. And honestly, it's usually worse than that. So yeah, we've hit a wall. A big one. To get any faster, we have to find a way to break that rule.
Villain number two is something we call the memory wall. Here's the deal. Over the past few decades, processor speeds have just gone to the moon, but the speed of our main memory, the DRAM, hasn't really kept up, so you've got this huge gap. Here's an analogy for you. Imagine a world-class chef who can chop vegetables at lightning speed, but their assistant can only bring them one ingredient every 5 minutes. What does the chef do most of the time? They wait. That's our processor, just sitting there, tapping its fingers, waiting for slow memory.
Okay, so those are the problems. How in the world did we solve them? Let's start with that CPU bottleneck. The answer all boils down to one key idea, finding ways to do more than one thing at a time. This is the core concept of instruction-level parallelism, ILP for short.
The first big weapon in our arsenal is called pipelining. Instead of treating an instruction like one giant task, we break it down into smaller stages. Think of it just like a car factory's assembly line. As you can see here, while one instruction is being executed, the next one in line is already being decoded, and the one after that is being fetched. So multiple instructions are all being worked on at the same time, just at different stations. It's a brilliant way to keep all the hardware busy.
Now, in a perfect world, this assembly line runs smooth as silk, and a brand new instruction pops out the other end every single clock cycle. But, of course, the real world is messy. What happens when one instruction needs an answer from the instruction right before it, which isn't even done yet? That's a data hazard. Or what if the program suddenly jumps to a totally different spot, making all the instructions we've started fetching totally useless? That's a control hazard. These hazards, as we call them, force the entire assembly line to just stop, to stall. And managing that requires some incredibly complex logic. Pipelining gets us close to that magic number of one instruction per cycle. But here's the crazy part. Modern processors blow right past that. So how is that even possible? How can you do more than one thing in a single clock tick?
The answer is a concept called a superscalar processor. And the idea is actually pretty simple when you think about it. If one assembly line is good, why not have a bunch of them working in parallel? A superscalar chip has multiple execution units, so multiple ALUs, for example. It can literally launch and finish multiple instructions in the exact same clock cycle, as long as they're independent.
And if you thought that was cool, this is where it gets mind-bendingly clever. To really get the most out of all those parallel assembly lines, high-end processors use what's called out-of-order execution. What the CPU does is it looks ahead in the code, finds instructions later on that don't depend on anything happening right now, and just does them early. It's like the ultimate project manager, juggling everyone's tasks to make sure nobody is ever just sitting around waiting. And somehow, it puts it all back together in the right order at the end, so the program runs perfectly.
So what's the big takeaway here? With techniques like these, we've completely changed the goal. We're not even talking about CPI anymore, trying to get it down to 1. The new game is instructions per cycle, IPC, and the goal is to get that number as high as possible, greater than 1. We've totally shattered that old performance wall.
Okay, so we've got this blazing fast processor that can do multiple things at once, but it's still stuck waiting on that slow assistant, our main memory. How do we solve the memory wall? The solution is honestly one of the most beautiful and elegant ideas in all of computer engineering, the memory hierarchy.
So instead of relying on one giant, slow pool of memory, we build a pyramid. Right at the tippy top, you have the registers. Super fast, but you don't have many of them. Then you have these layers of cache, L1, L2, L3, which are made of faster, more expensive memory. Below that is our big, slow main memory, and so on. The whole point is to keep the data the processor needs right now in the fastest, closest layers, to create the illusion that you have one giant memory that's as fast as the fastest layer. It's a trick, but it's an amazing one.
And hey, this isn't just some abstract idea. This is real. Let's look inside a real Intel Core i7. The L1 cache? Tiny, just 32 kilobytes. But it's so fast, the CPU can get data from it in just a few heartbeats, a few clock cycles. The L3 cache is way bigger, over 4 megabytes, but it's also a bit slower to get to. It's this constant, careful balancing act between speed, size, and cost.
But why does this work at all? Why isn't the CPU always having to go all the way down to that slow main memory anyway? It all comes down to one simple yet incredibly powerful principle: locality.
And locality basically comes in 2 flavors. First, there's temporal locality, or locality in time. All that means is, if you just used a piece of data, you're probably going to need it again very soon. Think of a loop counter. And then there's spatial locality, or locality in space. This just means if you access some data at a particular address, you're very likely to need the data right next door to it pretty soon, like when you're going through an array. Caches are built from the ground up to take advantage of these 2 simple facts about how programs behave.
So there you have it. We've just sprinted through some of the biggest, most profound ideas in modern computer architecture, the breakthroughs that conquered those bottlenecks and gave us decades of performance gains. Which kind of brings us to the big question: where do you go from here?
You can think of it as 2 main paths opening up in front of you. If you're sitting there thinking, how do I write software that can actually use all this crazy power? Then your path is probably computer science. But if you're thinking, wait, I want to be the one designing the next generation of these things, well, then your home is in computer engineering.
If you go down the computer science road, you'll get deep into operating systems, figuring out how they manage all this multitasking on multi-core processors. You'll study compilers and see the wizardry that turns our simple code into something the hardware can run at incredible speeds. And you'll learn that a good algorithm isn't just about theory. It's about designing code that plays nice with a memory hierarchy. Now, if you jump over to the computer engineering side, you're going even deeper. You'll be the one designing those multi-core processors of the future and dreaming up new ways to achieve parallelism. You'll learn the actual languages that describe hardware, that let you build these complex systems from the ground up. And you'll see how all these huge ideas get shrunk down to fit into the tiny, power-sipping chips that run pretty much everything in our modern world. So look, you started this journey by building a computer from the ground up, from first principles. And now you've gotten a glimpse of the incredible architectural magic that makes them so unbelievably powerful. The foundations are there. The map is laid out. The only question left is, which path are you going to explore first?